Okay, so let's see how to implement Borůvka's algorithm. It might be the simplest to implement because you don't need any external data structure. So the rule of the game is that we have a set T of edges that we have discovered so far, and we look on all the edges that we computed so far. It's a forest, right? There might, of course, be vertices that are alone. In fact, there might not be vertices that are alone. It's Borůvka, right? It might look something like that. That's quite possible. And first thing we do, we do DFS on the graph. This is the graph, not with the original edges, but with the edges of the forest that the Borůvka algorithm computed so far. So we do DFS, and we discover the connected component, and for each connected component, we number the vertices, right? So this would be 1, this would be 2, this would be 3, this would be 4, right? Every vertex would have this 4. Okay, so this takes O plus N plus M time. As usual, we are assuming that N is smaller than M, smaller or equal than M. So this is really O of M. So in linear time, you can number for every vertex knowing what connected component it is. Now, the second thing you do now, you scan, we're inside the loop. If this forest has a single connected component, we are done. We computed the MST. Otherwise, every connected component needs to vote for the cheapest edge that is adjacent to it. So we just scan all the edges in the graph, and every edge that in the graph, because we know which connected component the two endpoints belong to, we know we maintain the minimum edge connected to each one of the connected component, right? So every edge can be is a candidate for two connected components, and we can update the minimum edge in constant time. So in O of M time, we can compute for every connected component the cheapest edge adjacent to it. And now we just take all those edges and add them to T. Cannot be easier than that, right? So this is this step. And now we repeat, right? So clearly, this process of computing connected components, scanning the edges and so on, the inner loop, overall takes O of M time, right? So this is O of M time. Now, the important thing to observe is that when we do this process, every connected component gets connected to another connected component in every iteration, right? Because every connected component votes for the cheapest edge that it's connected to. Now, of course, you might have a situation where this connected component votes for this connected component, that votes for this connected component, and in fact, there might be another connected component that votes like that, and this connected component might vote back to this, right? So in fact, this is how it always looks like. It looks like a reverse tree, right? Except that in the top of this reverse tree, there's a connected component that votes for another connected component that also votes for it. So we have a loop, right? This, of course, is the same edge they vote for, right? So if this happened, for example, then it's great, right? 5 connected components collapse into a single connected component in the next iteration. But in the worst case, what happened is that every connected component votes for another connected component, which also votes for it, right? By that, I mean, they both choose an edge connecting both of them, and as such, those two connected components merge, right? So at the minimum, in the worst case, if you want, every two connected components merge into a single one, so the number of connected components decreases by 2 every iteration. We start with n connected components, right? So it goes to n over 2, n over 4, and so on, which means that the overall running time is n log m. Okay? And the nice thing about this algorithm is that no data structure, just simple graph algorithm and scanning of edges. So this is a very nice algorithm. And it's from 1926, as I said already several times, which is amazing. Okay, so this was the analysis of Borůvka's algorithm.